Okay. Hi, I'm Doehyun from KAIST.
And I'm Jakob Getz from University of Stuttgart.
Today we're presenting Wasm-R3, record, reduce, replay for standalone, realistic, and standalone WebAssembly benchmarks. This work was a collaboration with researchers from KAIST, University of Stuttgart, Google, and CMU. WebAssembly, or Wasm in short, is a portable, low-level binary format designed for compact representation and efficient sandbox execution. Its goal from the start was to bring consistent, near-native performance to the web. This was pursued because there are many demanding web applications, for example, for 3D visualization, audio software, and video games. So, if the goal of Wasm is to be fast, how do we actually know that Wasm is actually fast? This is usually done by employing some kind of benchmarks that exercises Wasm under various workloads. On the left is a figure from bringing the web up to speed with WebAssembly, presented in PLDI 2017, which introduced Wasm to the academic community for the first time. The paper states that, quotes, the results show that WebAssembly is very competitive with native code, with 7 benchmarks within 10% of native, and nearly all of them within 2x of native. In short, Wasm is fast. But 2 years later, there was an interesting paper presented named Not So Fast, presented in ATC 2019. If you, the gist of the paper is that if you only consider the PolyBenchC benchmarks on the left, Wasm indeed seems very competitive with native performance. But if you consider spec CPU benchmarks on the right, it is very clear that Wasm's speed is considerably slower compared to native execution. So, we can conclude that good benchmarks are integral for good representation of performance of Wasm. But do we have them? Unfortunately, that has not been the case. We believe this is due to a few challenges we have identified while doing this work. Firstly, manually creating and maintaining benchmarks requires serious engineering efforts. Secondly, porting existing native applications into Wasm through efforts like WASI is possible, but they are still lacking in maturity. Lastly, extracting benchmarks from real-world web applications require simulation of web host environments, but they are really, really hard. We found one technique in the literature that is able to automatically generate benchmarks from arbitrary execution, which is record and replay. But we found existing text to be lacking in many ways to directly apply in our situation. For example, pinplay, although it supports recording of cross-architecture, it doesn't support replay across architectures. JSBench on the second column, it doesn't track all the memory loads and stores to the memory, so the execution might diverge from the original execution, leading to inaccurate replay. And Jalangi supports record and replay of only JavaScript applications. To solve this problem, we have designed and implemented Wasm-R3. Wasm-R3 is the first record and replay technique for Wasm. Wasm-R3 supports recording at any major web browsers and then produces replay benchmarks that are replayable on any Wasm engines, web or non-web. How does Wasm-R3 achieve this goal? Here's a bird's eye view of 3 R's of Wasm-R3, which are record, reduce, and replay. Record phase accepts web applications with Wasm as an input and generates a trace. And then reduce phase reduces and optimizes this trace into its reduced form, which is, of course, a reduced trace. Lastly, replay phase generates something replayable, a replay Wasm from this reduced trace. I want to take a little bit deeper look into each phases. Firstly, record phase takes as an input a web application consisting of a WebAssembly module and a host JavaScript code. And then, when this host JavaScript code tries to instantiate this WebAssembly module, it intercepts the module and then applies bytecode instrumentation onto this WebAssembly module. And with this instrumented Wasm module, you run it inside the record runtime, which tracks all the function calls and returns and all the mutations to the states of the Wasm module, which leads to a generation of a trace. But for real-world web applications, this can grow to be really, really large. Thus, we apply two kinds of optimizations, which are shadow memory optimizations and call stack optimizations, making an optimized reduced trace. Lastly, in the replay phase, we first turn this optimized trace into a replay IR, then apply several optimizations onto this replay IR, and last, we convert this optimized replay IR into a replay Wasm module, and we combine this with the original copy of Wasm module, leading to a standalone executable replay benchmark replayable across any Wasm engines.
All right, so let's go over those phases in a little more detail. So we decided for the record phase to use a bytecode instrumentation of the Wasm module. The benefit is that we don't need to modify any virtual machines or the browser, which makes us very portable. On the left, you see the trace model. So basically, a trace is nothing else than a sequence of events. Events can be of two kinds. There are function, entry, and call related events. And there are events that relate to WebAssembly internal objects, like for example the memory. For function-related events, we need to track which function they are, and also consecutively we need to track values like parameters and return values. And for object-related events, we need to track information about those object changes. For example, for a memory load, we need to trace the address and also the value that got loaded from that address. As we said already, this trace can grow very large, so that's why we applied two optimizations to the trace in order to reduce the number of events contained in a trace. One of those optimizations is shadow memory optimization. This works by introducing another data structure, which we call shadow memory, to the original WebAssembly module. And the algorithm works in a way, so when we encounter a store inside of the WebAssembly module, it will update both the actual memory and the mirrored shadow memory. If we encounter a store in JavaScript, it will only update the actual memory though. So this information we can then use to filter out events in the trace. So on every load, if the actual memory and the shadow memory state are the same, we can safely discard this event because it will be redundant. If they are different though, so if actual memory doesn't match the shadow memory, we need to actually keep this event in the trace. Little example here, so we have here a little example trace. You see up there in the first two lines, we have 2 times the same load, loading from the same address, the same value. And the second thing is basically redundant. So this is one pattern, for example, that gets filtered out by this algorithm. The second optimization we made is the call stack optimization, and this is to filter out any sort of function call related events that are not necessary for the replay generation. So basically, if we have a WebAssembly function calling internally of the module another WebAssembly function, we don't actually need the information because it doesn't interact with the host environment in any way. We just need to keep those function calls, which are like actually calls from an internal function to the host environment, or the other way around if we have a host function calling a WebAssembly internal function. Lastly, in the replay phase, we use this optimized trace to generate the replay. So here on the left, you see an example trace. You see 4 loads. So the first load event loads the value of 3 from the address 0. The second load loads the value of 2 from the address 4, and so on. And this will generate the following replay code. In our case, in the implementation, it's a replay IR, but here I display this by actual WebAssembly instructions. So basically, in the replay code, we need to consecutively just load from the address 0 the value, just store to the address 0 the value of 3, store to the value of 4, to the address of 4 the value 2, and so on. As you can see here, this is not quite very effective because we use a lot of I32 store 8 instructions. We may very well combine those into one bigger instruction like the i32 store, and that way we can optimize it and end up like on the right side with very optimized code for this trace. So let's talk a little bit about the evaluation we conducted. So Wasm-R3 is actually implemented, and we tried it out on several web applications that run in the browser. So we were asking ourselves, how applicable is Wasm-R3? We also asked some performance questions, and also like how close are the replays to the actual original applications. And we asked ourselves, how effective are actually those reducing techniques we applied for the trace. We also evaluated the effectiveness of our replay optimizations, which I will not go over in this talk because of time reasons. So first, the applicability of Wasm-R3. So we had a website online which is called, I think, madewithwebassembly.com, which has like a huge list available, of Wasm applications. So from this list, we systematically filtered out 43 web applications, and we got 27 successful runs, which is a success rate of 63%. The reason for that is that it's requiring a huge engineering effort to actually make Wasm-R3 run on arbitrary applications, because web applications tend to be very complex. Next, some performance measurements. So we measured the recording overhead, so how much is the slowdown during the record phase. In a mean, we observed a 3.4x slowdown. For the best cases on the right, you can see we almost observed no slowdown at all, but for a very bad case, here Boa on the right, on the left, we observed a more than 16x slowdown, and this is due to many interactions with the host environment. We also measured some performance characteristics about the replays we generate, which also serves as like how close are the replays actually to the actual application. What we show here is like the number of CPU cycles spent in the replay code versus the original Wasm module in our replays. And we can see here for all of those applications, most of the cycles are actually spent in the original Wasm module, and only a few cycles for most of the application, really like, you cannot even see it, is spent in the replay code. Then we also evaluated the effectiveness of the trace reduction, how effective is that basically. And so if we only apply the shadow optimization, the shadow memory optimization, we end up with a trace that only has 27% of the original trace entries. If we only apply call stack optimization, we end up with a trace only containing 38 of the original trace entries. And then we put both optimizations together, all of them together, we only have, in the mean, 0.47% left of the original traces that are in the large trace before the optimization. Yeah, so let's conclude the talk. So Wasm-R3 is the first record and replay technique for WebAssembly, and we sincerely hope that this improves the state-of-the-art Wasm benchmarking. It is available as open source, and we also have collected a little benchmark suite which we call Wasm-R3 Bench. It's also available online. And yeah, thank you very much for your attention. If you have any questions, feel free to ask or write us an email.
Cool. Very cool work. Could you explain a little bit why this fails? Like, I didn't quite follow.
Yeah, sure. Do you want to explain?
Sure. We've actually broken down why these fails into like the reasons, and 1/3 of the failures was due to dependency limitations. For example, we use some kind of a bytecode instrumentation library, but they don't support up to latest Wasm specs. So in this case, instrumentation could not happen for these kind of reasons. And 1/3 would be like mainly our implementation reasons. For example, the Wasm function has a limitation of how big the code can be. So, and we do some optimizations to work around the problem. But there are some cases that doesn't work. So those kind of are 1/3. And like last 1/3 are we couldn't actually find out the cause of that. So if you want more detailed cause, you can refer to the paper.
Hi, really cool work. Have you considered, so most of the functions that you record are deterministic. If you always call them in the same environment, they will do the same thing. So you could just not record them and keep the code and just call them. So with that in mind, have you considered just recording the non-deterministic parts of Wasm? So the parts that read data from the environment that needs to be recorded to be replayed correctly, and everything else just keep the code and run it?
I think I didn't understand the first part of the question is, are you saying that the Wasm code on the recording, they are non-deterministic?
Deterministic.
Deterministic.
Yes.
But like, wouldn't the behavior of the function change with respect to behavior of the host code? That's.
Imagine a function that has an element to a list. Regardless of the environment of the host, given a list that's empty, this function will add one element to it. So why do you record it? You could just not record it and run it.
So I can try to answer. So actually, like recording to a list is actually just a manipulation of, or like adding something to a list is a manipulation of the memory in WebAssembly. And anytime we exit the WebAssembly module and call the host code, this host code can do some manipulation of the list which we don't know of. So each time we actually change the memory or read from memory, we have to check, did the host code before run and did it do something to the memory? Because at the time we are actually doing the load or doing the stores, we don't know. So that's why we have to collect all this information. And to filter out all the redundant stuff that actually we knew, afterwards we have the optimizations.
Okay, I'll talk to you later. Thank you.